Hello and welcome to another episode of Fresh Thinking by Snowden Optiro. This is the first of 7 podcasts, and we're talking about modern understanding of resource estimation techniques, and we'll be talking about their strengths and limitations and describing a new technique. My name's Ian Glacken. I'm Executive Consultant at Snowden Optiro here in Perth, and I'm joined by Susan Havlin, who's Managing Consultant of the Geology Group here in Perth. Welcome, Susan.
Thank you.
So this is, as I mentioned, this is a series of 7 podcasts, and we're talking about modern approaches to resource estimation. Talk about conventional approaches like ordinary kriging, and then we're going to talk about recoverable resources. We'll explain what they are, and we'll talk about the role of conditional simulation, not only in recoverable resources, but also the additional information that simulation gives us over and above resource estimation. So it's quite a lot to explore. And in this first episode, we're starting with the foundations. So let's talk about where the industry's at with resource estimation techniques. Susan, so how reliable would you say modern resource estimates are?
Look, I think modern mineral resource estimates are generally very robust, particularly from a technical perspective. So over many decades, the industry has developed strong standards around sampling, geological modelling, estimation methods, and reporting frameworks such as JORC and NI 43101. So techniques like ordinary kriging have been used successfully for many years and remain the backbone of many mineral resource estimates. So these methods provide statistically sound estimates that are consistent and generally repeatable and well understood by competent people in the industry. So, however, like any modelling approach, every method has its strengths and limitations, and it's important that we understand where these limitations might influence how the deposit is represented.
Right. So let's dive a bit more into ordinary kriging. Ordinary kriging, as you mentioned, has become the standard. And in fact, in a survey carried out in 2024 of the 2 main markets, that's the Canadian market and the Australian market, 63% of the resources that were publicised were done by ordinary kriging. So why is it the standard, and what are the advantages of using ordinary kriging?
Well, it has several major advantages. And I should also point out that last year I had I was a CP in a lot of releases, and probably 99% of them were ordinary Kreg models. So I'm very supportive of the ordinary Kreg model.
Glad to hear it.
But it does have several major advantages. So it produces, as I said before, the estimates that are statistically optimal given the available data, and provides results that are consistent across the deposit. It also fits well with established resource estimation workflows and reporting requirements. It is very robust and can handle high variability or skewed data better than some of the other estimation methods. So because of these strengths, it's become the default estimation approach for many deposits around the world. So it works particularly well where grade continuity is reasonably well defined and where the mineralisation behaves in a relatively predictable way.
Yes, what I would say, the second most popular estimation technique is inverse distance, and the big difference, as you well know, between inverse distance and ordinary kriging is that ordinary kriging is based on the continuity model or the variogram. So from that point of view, it's as you say, it's quite robust and quite reliable. So, having said that, where do you think that ordinary kriging struggles?
Well, I mean, one of the well-known characteristics of kriging is that it tends to smooth grade variability. So, and I say smoothing. I'm not saying smoothing is a bad thing. Like, we need a level of smoothing, because we are estimating interblocks which have less variability than the points. But sometimes OK can suffer from over-smoothing. This happens because the estimate combines information from surrounding samples to produce a prediction of the grade. So the averaging process reduces the extremes in the grade distribution. So the high grades tend to be underestimated and the low grades tend to be overestimated. So the results is that the block model often appears more uniform than the actual raw drill hole data would suggest. Another issue with OK in particular is that when we're extrapolating beyond the limits of the data, we have if you have a grade 10, so is it increasing at depth or is it decreasing at depth, then the OK estimate will obviously follow this trend. So one consequence is that in the areas away from the drilling, we could tend to overestimate the grade or we could underestimate the grade.
Yes, we do get some artifacts sometimes as a consequence of the algorithm, which does extrapolate trends upwards and downwards, as you say. Another issue with ordinary kriging is that it is possible to get grades in the blocks that are higher than the samples, which is sort of not what you would expect, but you can get that, and it's a little bit awkward. And very occasionally, as you know, we do get negative grades. That's not to say that it's bad, but there are some issues. So let's talk about this idea of smoothing, and then the counterpoint, which is this idea of short scale variability. Why is it important to?
It matters because mines operate at the local distribution of grades, so not just the average grade. So mining takes place at the scale of the selective mining unit, or the SMU as we call it, which is often smaller than the blocks in a resource model.
And how would you define the SMU?
SMU is probably usually from talking to the client, talking to engineers, figuring out how they're actually going to mine the deposit, what's a logical size on the block. So usually it's a collaboration with client engineers
Right.
to come up with the SMU. I mean, obviously the SMU is was usually smaller than the parent block size, which is related to your drill spacing. So grades can vary significantly at the SMU scale. So when decisions such as mining selectivity, cutoff strategies, scheduling can all be influenced by how accurate the model represents that variability. So understanding how estimation methods represent short-scale grade behaviour becomes important when the model is used for planning and evaluation.
Yeah, so this idea of short scale variability and the SMU represents the selectivity of the mining operation, whether it's open pit or underground, and we need to obviously try and predict that selectivity at the time of estimation. So this brings us on to this idea of a recoverable resource. So what's a recoverable resource?
Well, a recoverable resource aims to estimate the grade distribution that would be recovered during the actual process of mining. So rather just than the average grade in the ground, we're trying to predict what the grade at a point is going to be at the ground, or an area in the ground. So traditional resource estimation methods predict the expected grade of blocks in the deposit, but a recoverable resource approach recognises that when you're mining occurring at a SMU scale, the grades encountered can behave quite differently from what the block average is. So these methods attempt to estimate how grades are likely to be distributed when mining takes place, especially when we're dealing with data that is like more widely spaced than required for the SMU scale estimation.
Yes, which is often the case at an early stage. And in fact, it's only when we get to the grade control drilling stage or the grade control estimation stage that we have the final set of data. So we do need to predict the behavior of the model at the scale of mining, the SMU.
Yeah.
So is it really about choosing the right estimation method for the purpose of the model, whether it's a resource estimate or a more detailed estimate?
Yeah, well, yeah, because different estimation approaches are designed for different objectives. So some methods are very effective for producing stable resource estimates suitable for reporting. I mean, especially very early stage deposits.
Yep.
While others are designed to better represent the recoverable grade distribution at the mining scale. So this is probably, when we've progressed, done a few drilling programs, you figured out it's going to be viable, then sometimes you do need to move into more of a recoverable resource. So understanding those differences is important when deciding like what model and what it's going to be used for.
Right. So that basically sets the scene for the rest of these episodes, this idea of getting the right estimation technique. So one thing that we need to recognize is that the distribution, as you say, the distribution of the grades at various scales is different depending on the drill spacing and what we're at.
Yeah, definitely.
Okay, so this first episode of 7, we've introduced the issue of or estimation, ordinary kriging, which is the most popular technique, and this idea of smoothing or over smoothing, which is quite easy to achieve. And then this idea that when we get to the grade control spacing and the actual mining spacing, the distribution of grades is different, and how can we predict that? And we've introduced the topic of recoverable resources as one way of doing that. In the next episodes, we're going to go on to talk more about these recoverable resource techniques. So thank you, Susan.
Thank you, Ian.